The Insider's Guide to Energy podcast is proud to announce the Data Science mini-series in collaboration with Force, problem-focused and solution-driven. On this show, we will be covering everything from data science fundamentals to trading, forecasting, working with large data sets, and even skills required. Make sure to follow us on Spotify or Apple Podcasts so you don't miss out on new episodes.
Welcome to Insider's Guide to Energy, Energy Data Science mini-series. Today we have with us Dexter Energy. With me, I have Tom Lemmens and Hubert Penn. Welcome to the program, guys.
Pleasure to meet you.
Thanks for having us.
It's a pleasure to have you both here today. I think it makes sense to start out by a little bit of what your company does in the analytic space and in the energy space to help us understand.
Yeah, sure. So we're Dexter Energy. We are a forecasting and trade optimization software as a service company. We cover the short-term trading cycle in the power domain, and we do this for the renewable energy traders in Europe. So these can be renewable off-takers that are providing PPAs, or renewable asset owners that have their own trading capabilities. We are now with 50 people. We just raised a Series B investment round this spring, so we're growing it to 80 people at the end of the year. And so really we're a software company that build data science products for the power domain in the short-term trading cycle. We're heavily focused on data science and machine learning. So 80% of our team is either a software engineer or data scientist.
And when you say you're in the renewables, in the trading, maybe help a little bit more of what it is you do specifically.
Sure. So in principle, we help our clients to manage and reduce imbalance costs. An imbalance cost is a cost that is there because as a renewable trader, you're not providing the power you've been selling on the market on the day ahead. And that comes at a cost, and that's what you're trying to minimize. And you can do this in two ways. So roughly put, there's two product categories that we're providing. One of them is generation forecasting, so forecast as good as possible what a solar or a wind portfolio will be producing on the day ahead, but also in intraday. So you can change your position based on an updated forecast. And then the other one is you want to have an idea whether the prices in the future are going to be higher or lower than on the day ahead. So if the prices are going to be higher, you might want to sell a little bit more on the intraday or on the imbalance markets. And if you think that the imbalance prices are going to be lower, closer to the moment of delivery, then you want to sell a little bit extra on the day ahead in order to be potentially buying back some power at a lower price. So really what we're trying to help our clients is to provide a forecasting and trade optimization solution, so suggestions what they should do in order to minimize volumetric risk and maximize trade profits on the day ahead, intraday, and real-time markets.
So from the cheap seats, it sounds like magic, right? So you're going to predict where the market's going to be ahead of time. Now, you do this with weather forecasts. Is that the main tool in your tool belt?
So in principle, we have three different categories of input data. And the first one definitely is weather data. So we are connected to all relevant weather data providers or weather forecasts that are out there. And we also spend considerable time to benchmark and test these weather models and understand which models are good at what job. And what job can mean, are they good in solar irradiation forecasting or in wind speed forecasting? Are they good in the north or in the south of Europe? And are they good 1 hour ahead or 1 day ahead of time? So that is one category. The other category is market data. And so if we are going to build a price forecast, of course, we want to know what other aspects are happening in the market other than just what's happening with the weather. And then the third one is if you want to provide a generation forecast to a company that is trading their renewables portfolio, you need to know what is happening in that portfolio. So we are also receiving data from our clients so that we can provide that generation forecast.
And then what kind of magnitude, you have three sources. It sounds like it could be quite a bit of data. So what kind of magnitude and type of data are you actually receiving and working with?
So the magnitude of data is, so first of all, everything is a time series and almost everything has a location. This matters because typically just regular time series data isn't particularly high volume, especially things like prices. However, there are things that are high volume. For example, weather data, right? So like Hubert said, we process a lot of weather forecasts, and weather data is very high volume data because it covers a grid and multiple height layers, multiple or many variables, like Hubert said, so radiation, wind speed, temperature, across different time steps. So that's why this volume is so large. And you should think about gigabytes per day, like hundreds. That's high volume data. The other high volumetric data is trade data of intraday trading. So logging the order book of the intraday, for example, that's high volume data.
And then what kind of things are you doing to the data to get the kind of forecast you want? How does the process work? What's happening there?
So we do essentially two types of things, right? So we're in the forecasting, the time series forecasting business, and then the optimization business. Optimization part is where you optimize on the best action you can take. And what we do with the data is essentially there's all these statistical learning steps throughout the data science cycle, right? Or the machine learning life cycle. So all the way from ID, right? Exploring the data to wrangling the data in the right format, filtering the data, filtering outliers, really understanding what's in the data, to then the actual statistical learning step, right? The curve fitting, the forecasting step, to the next step after that, which is the decision-making step where you optimize on in a certain decision space, like trade now or trade later, trade volume X or trade volume Y. And then after that, there's the evaluation step. That's the typical steps that are taken. And we do this for generation forecasting, right? So that's forecasting megawatt hour per market interval, typically 15-minute blocks. And then the same for price forecasting, but then euros per megawatt hour. And we do this from now up to a couple of days ahead. That's sort of the task, sort of the technical task we execute on. And a few concepts that we really care about is, first, we really care deeply about data quality, right? So we invest a lot of time, attention, love, and care into making the data as well behaved as possible. So we get historical data from customers, like we just said. So that's historical production data of a wind turbine, for example. Now we get the time series, and instead of just blindly using this, we invest a lot of time into really understanding why does the time series behave as it does. So what type of maintenance periods are there in this data, and other special events that make the data behave differently than you would expect from just looking at a wind turbine, right? The second step is that we combine this statistical approach, right? This machine learning data science approach together with domain knowledge. So for price forecasting, this is a very deep understanding of what is driving the markets and how do you model this. And for generation forecasting and also price forecasting, a deep understanding of meteorology, but also the engineering behind a wind turbine or a solar panel, because we are convinced that where the actual value lies is like combining both worlds, right? So the physical understanding of what's happening together with the statistical skills to be able to model it.
And then how do the traders consume and use your data? Are they just receiving APIs and putting it into their own scripts, or what are they doing with it?
So basically, they receive our forecasts and our data, and they try to, or they trade on it. So they take positions on day ahead and intraday, and sometimes even real time in a few markets. So what their goal is initially is to have a volumetrically accurate position as possible. So optimize for volumetric imbalance volume to get that as small as possible. And you do that by having a optimal generation forecasting setup. And what we mean by optimal there is that you might have multiple forecast vendors that have certain opinions of what your portfolio will do tomorrow in every hour. And then you have a more or less sophisticated optimization step there to be choosing the best forecast for the certain job. And this can be either manual, so you compare vendor 1, vendor 2 with vendor 3, and you decide vendor 2 is the best at wind and vendor 3 is the best at solar. So that's what you are going to nominate on, or that's how you're going to sell your power on day ahead. But you can also do it one step further, where you say, I realize that vendor 1 is really good in low wind speeds, and I realize vendor 3 is really good in high wind speeds. So I add an optimization layer, and this can be rule-based or more advanced, where you say, I'm going to use vendor 1 for low wind speeds and vendor 3 for high wind speeds. So you start mixing those vendors and you start exploiting the weaknesses and the strengths of these different vendors. And then in another step, you could even just use all of those vendors and throw them into a larger machine learning model and let the model learn itself what to do. That's what we call ensembling, and that's something that we also see happening a lot on the weather forecasting side. So you have different weather forecast providers that have different scenarios, and you put a machine learning layer on top to basically try to find a optimum based on those different forecasts and based on that specific situation. So minimize imbalance volume is the first step that our customer would do. Then the second step is trying to take a strategic position and deviating from that expected lowest imbalance volume to optimize your trade revenues. And what I mean by that is that the spread of the price between day ahead and real time can be asymmetrical. So there can be a significant risk that the price is going to be a lot higher than it can be lower. And so when you have a probabilistic price forecast, you can exploit that by shifting your position a little bit towards exploiting that future high price. And so basically what they're trying to do is they take a view on the generation forecast, they take a view on the price forecast, and they optimize the two into a strategic position. And this is actually a service that we are providing to our customers, helping them to basically optimize the profits on day ahead, intraday, and real time. And when we move away from day ahead, we go into the intraday cycle, which is a continuous market. And there you've just received an updated generation forecast from your different vendors, and it appears that your position is long or short. So you know that you have an open position in imbalance. And now it is a matter of deciding, do I want to close this open position in imbalance on the intraday market? Or do I wait and do it later? Or do I not close this position at all? And in order to make that continuous optimal decision, you always need to know what is your open position. So that's based on your generation forecast, on your volumetric forecast. And what do I think is happening with the market? And I do this using a price forecast. And if I have those two, I can combine them into an optimal trading strategy. And that's basically what our customers are doing 24/7.
So you mentioned in the intro that your team is made up with heavy data science team, I think, is what we've talked about. So you're in the data science business. We've talked about the importance of having well-behaved data. I think is the word that you said. You wanted well-behaved data. How else is the machine learning? And let's peel some layers of the onion back and see some more of what you're doing and how a data science team is helping solve these kind of problems.
Yeah, sure. So the steps I mentioned, right? So in the end, we care about like working backwards. You care about the value you add in a business process, right? So that's in the trading cycle. And to do that, you care about accurate forecast. So how do you get to accurate forecast? And economical trading decisions. So how do you get to that point? And for the for the generation forecasting part, like I said, so one of the key things is to really, like with any machine learning problem, it's about understanding what drives your data, right? So what's in there? Because as soon as you have data that you have a very deep understanding of, you understand the domain or the physical processes behind it. Typically, the curve fitting part isn't the difficult part. It's about understanding the domain. It's about understanding what's in your data, right? So really investing in data quality. Then there's the curve fitting part, right? So for instance, fitting the part between wind speed and power output. And the other challenge is essentially the software engineering components that glue everything together and that expose your product to the outside world. Now, some of the problems that the team is working on to get to this is, for example, automatic data quality checks, right? So filtering data based on anomalous behavior. We invest a lot of time and effort into that to really filter out data or to clean up data that you don't want to have end up in your trained model, right? Because you don't think it's representative for the future, for example. The other thing that we obviously do is the curve fitting part itself. So that is exploring the relation between, again, wind speed, wind direction, air density, and power output. There's all sorts of tasks that we have to do there. First of all, is just sort of making a point estimate, right? Like an as accurate forecast. Other things you can do there is output probabilistic forecasts, right? Like Hubert just explained. So you don't just output a single point, but you actually recognize that there's a lot of uncertainty in what's going to happen, and you try to model for that, such that you get a distribution as output instead of a single point. And then there's the optimization space, right? So how do you make an optimal decision? And for that, it's really important to understand what you think is important, right? So how do you define your loss function? What do you want to reward and what do you want to penalize? You can steer on risk averseness, for example. So like Hubert said, you can take into account the distribution of expected prices. And if there's a certain skew in your data, so for instance, a very long tail in high prices, you can take this, or negative prices, you can take this into account when you're making a trade decision, when you're optimizing for a trade decision, by taking into account this distribution. You can steer on risk averseness, right? So when you decide on an action, that you penalize large losses extra, right? So you can design your loss function like that. And this is what you typically do in an optimization step, right? You think deeply about what is your exact loss function, and then you try to optimize for that. So these are some examples of the machine learning, typical machine learning tasks. And there's niche problems as well that we solve. An interesting fundamental problem there is, for instance, we got fairly good at forecasting icing on wind turbines. So there's, if it's cold, if it's humid, there can be buildup of ice on the leading edge of a wind turbine blade, right? There's just ice deposition on the blade. Because of this, you typically shut down the wind turbine, or there's at least an efficiency loss. And we try to forecast this. This is a very good example of where you need to have a very deep physical understanding of what is causing this, as well as needing to have a very good understanding and skill capability to analyze data and to actually model for this. This was a very hard and complex one to solve.
So with the icing example, I could see how that could change or be a risk to someone. So if you could predict that, how big a data set historically do you need compared to how much future looking from weather do you need to do something like that? What's the balance of, I need lots of historical data to figure that out, or is that a smaller historical set and more of a predictive set?
So for any typical supervised machine learning task, you need labels, right? You need labels to train a statistical model on, to be able to recognize it next time it happens. You say, hey, I've seen this before. Probably it's icing again now as well. So you need labeled data. And in this case, getting labeled data is a fairly specific task, right? Because icing does happen, but it doesn't happen every day, fortunately. So you need to go and get the data. And in this case, there's with typical machine learning tasks, there's this curve, right, where with more data, your model gets more accurate. And at some point you're in the area of diminishing returns. So for this, we actually needed quite a lot of sample events, right? We needed labeled icing events to be able to model this. Yeah.
Yeah, and to generalize this a bit more away from the icing, so this is actually also an important part of the research that we have to do. How much historic data do we want to use in our modeling? And sometimes you also don't even have data. To give you an example, if we have a client who is ramping up an offshore wind park, and there is no historic data, you need a physical model to jump in because you're not able to model it statistically because you don't have any historic data, right? And then comes the challenging part of, when do I switch from a physical model to a statistical model? Do I do that at 100 days of data, or at 200 days of data, or 50 days of data? So I want to understand how good is my data in the first 50 to 200 days, and where is that flip over? And I can also actually blend it. So I can also say, okay, at 20 days, I do a 50-50 blending. And then later I move more into the statistical model. And so, for example, on our wind forecasting, we have 4 different models that are running in parallel. And then there's a machine learning layer on top that basically decides, based on how much historic data I have, do I want to blend the different models together to get an optimum result. And to give you another example that can be a trade-off, and we have to think long and hard how to do it, is when you look at price forecasting. So imagine today, the 21st of June, we want to predict what the imbalance prices will be tomorrow. So of course, we're interested in what happened last year in June, when the sun was high and when the weather was good. So we try to look for similar days. But at the same time, the world has also changed, right? So this is another season. It's another year. We have another day ahead price. The geopolitical situation has changed. So do we actually want to do we actually model our price forecasting based on a lot of historic data? Let's say on the last 2 or 3 summers, and look for similar days? Or do we actually use a more near-time forecast and basically look at all the regressive behavior, what happened in the last 2 weeks, let's say? And then there comes a part where you want to make a decision in how you optimize those two, or how you combine those two into your price forecast. And there it really matters how much historic data do I want to use. Ultimately, for a data scientist, it's about having as much data as possible, because it gives you modeling freedom, right? So the more data you have, the longer history you have, the more opportunities you have in choosing certain features and certain model designs.
So speaking about data volumes, and you talked about it before, how granular do you go down into the weather forecasting then?
Typically, weather forecasts have a set granularity, both in terms of geospatial resolution, right? So highly accurate weather forecasts at this point are like on a 1 kilometer resolution, like one of your previous guests also talked about. And then like more global models are on the order of magnitude of 8 or 10 kilometers. And then the typical temporal resolution of those models is 1 hour. And for some models, it's 15 minutes. But that's the order of magnitude you need to think about.
So, for example, a microclimate event, would that affect one of your traders? And is that something you're trying to predict? So maybe too much wind for a turbine where it might have to shut down the blades or whatever, not to disrupt. Are those kind of things that you're targeting?
Oh, yes.
So maybe help us understand that. Other than, oh, yes, maybe a little bit more explanation.
Yeah, for sure. Yeah, so these type of events, right, that's anything that's out of the ordinary, that's typically what drives prices. And that's what, like all the unforeseen events, that's the stuff that hurts most on the market. If no one sees something coming, like a thunderstorm in the Netherlands yesterday, there was this big cloud passing over, a lot less solar production. The timing of this day ahead, even intraday, is very difficult to predict, as well as the impact of it. And these are the type of things that in a more weather-dependent system become more and more important to be able to handle. And this is also the reason why you see more and more of the trading volume moving to shorter horizons, right? Like hours ahead instead of weeks ahead or years ahead. And so some of the events that matter are the one I just discussed, right? Like a big change in radiation impacting solar output during daytime. Another one that's very interesting is a weather front, like a high wind speed weather front, right? Is it going to be just over or just under the cutoff wind speed of wind turbines, which usually have a cutoff wind speed? Now, for modern large offshore wind parks, this is usually gradual now, so it's not a certain like hard shutdown point. But those are really the type of events that are important to forecast. Icing, I just mentioned. These are very impactful, and we try our best to model those as well. As we know, these are the few events that make or break a year in the life of an energy trader.
So as renewables become more and more mainstream and scale up, and markets might get to shorter trading windows as we go forward with more renewables, how do you avoid being that frog in the pot of boiling water, the temperature coming up? How do you monitor longer term trends or things that might be changing because suddenly there's considerably more renewables changing the rules, right? Is that something that, based on what you've already described, just catches itself because you're always kind of looking for the shorter models? Or how do you make sure that there hasn't been a holistic change in the system over time as you're doing this?
Yeah, so I'd say there's two things that are two categories that are impacting the market. One of them can be more gradual. So, of course, the geopolitical situation impacts gas prices, and since often gas plants are the marginal plants, they dictate what the power prices will be as well. So, whatever the commodity prices are doing, gas and coal and CO2 are having an impact on the day ahead market. And the day ahead market, again, really impacts what is going to happen on intraday and imbalance. So you can imagine that imbalance prices, for example, that they fluctuate around the day ahead price. But you see another effect, which is when day ahead prices inflate, the imbalance prices inflate even more. And what you get is that the spread between imbalance and day ahead in absolute terms actually increase significantly. And therefore the pain also increases in managing those imbalance costs, because if you have the same error in imbalance volume, but if your imbalance price is much larger, you're exposed to these high prices, and that can become very costly. And what we've actually seen in our core markets is that, so if you look at 2016 to 2022, the year-on-year average solar and wind increase in terms of installed power in a country was 10%, but the imbalance price spreads actually increased by 60% year-on-year. And this really is so it's really a non-linear behavior. And what we are foreseeing is that until it gets better, it's going to get more challenging, because we are now installing huge amounts of offshore wind and solar behind the meter, right? So that is also driven by the desire of Europe becoming more independent when it comes to power production. But that is it doesn't happen from one day to another one. It's more a gradual process over months, and that's something we are able to foresee when we make a price forecast. So we learn from those evolvements, right? We learn those price evolvements, and that's actually what you want to become good at, right? So you want to spot the trends and trade on them. Then there is the other category, which can be a bit more changing from one day to another. So, for example, the implementation of MARI and Picasso, which is a certain regulation change on how balancing services work in the European market, and that can be a challenging thing, because what it can mean is that you need to backfill data which is not valid anymore, or you have to shorten the amount of days that you have, right? Because it can be a totally new situation after a certain implementation like that. Usually what we see is that we are very fast in learning, and usually faster than the market. So anecdotally, we learn that when there's a market change, we're able to pick this up quickly, quicker than the market, and therefore usually our clients are very happy after there's been a market change.
So you mentioned one other thing that I don't think we've talked about is, what regions are you currently in? Where are you doing all this?
Sure. So we are eventually aiming to become a global player, but the intermediate step is to be present in Europe. And right now we are active and have paying customers in the Netherlands, Belgium, Germany, Italy, Romania, and the UK. And next up will be the Nordics, but also Eastern European countries like Poland, and also the Iberian Peninsula is on the roadmap for the next 15 months.
That's quite a diverse segment. What are some of the nuances or differences between market to market that you would need to consider, maybe from your data, or your models, or what's different from market to market from a data science point of view, perhaps? Yeah,
so I think what differentiates us a bit from other power forecasting vendors is that we do trade optimization. So we combine power forecasting and price forecasting into optimizations. And when you look at price forecasting, what happens in a local market can be a bit different from one market to the other one. And so that's why we look at expansion from one country to the next one, whether it makes sense. And the attributes that matter there are there imbalance problems, and how big are they? And usually that is driven by how much renewables there are and how much renewables there are being installed. But also if the market is liberalized and if there are inefficiencies, and also how much flexibility there is. So, for example, if you look at the Nordics, it's a very efficient market. There's lots of players, which is interesting. But on the other hand, there is so much hydro, which brings a damping effect on the imbalance price, because there is a lot of hydro flexibility. If you look at, for instance, Romania, there is enough players to have a market with liquidity, and there is quite some renewables. And the imbalance costs are really high, so there is optimizations to be done, and that can typically be a very interesting market for us. And then when it comes to localization of what we do, I think a key factor that changes from one country to another one is indeed weather models. So you have global weather models like GFS and ECMWF, and generally, if you're in the forecasting business, those are the first two models you are going to onboard. But everyone has them, so if you trade on these models, then you don't have a competitive advantage with the rest of the market. So you want to decorrelate yourself towards what everyone else is doing. So then the interesting part as a data scientist becomes is about benchmarking different weather models, right? Looking for local weather models or looking for third-party players who provide their own weather model. An example would be an earlier guest you had on the show. And then benchmark private weather forecasting solutions with the general ones. And so loosely put, you can call these A/B testing. And so given a certain task, so like Tom said, given, for example, wind speed in a certain location, given a certain ahead time, how good is one solution versus the other one? Does it add signal? And is it worth the juice to squeeze in terms of onboarding that model and operationalizing it and putting it into our data lake and have team MLOps making sure that runs well operationally. And that is a challenging task for every country, finding those best weather models and onboarding them.
And then how big or what kind of scale are we talking? So IT infrastructure, storage, you just talked about a data lake of yours. You also talked about huge amounts of data coming in every day. Maybe let's talk a little bit more about the technology that's supporting that.
Yeah, sure. So one of the key things you have to consider when you're hosting a forecasting and optimization product like this is your machine learning infrastructure, right? So in terms of technology, like we use a cloud provider, and in general, I think it's usually a wise idea to leverage as many of their managed services as is technically wise, right? Like it's you stand on the shoulders of giants, so to say, because they put so much hard work in those managed services. So we use a lot of those in terms of managed storage solutions, but also all the other things you need. And then what you typically have to invest in is your like the data infrastructure, but also in the machine learning infrastructure, right? So the infrastructure you need to be able to train and release machine learning models at scale, right? Because there's a lot of models that we have running in parallel. And a step before that, it's also very important to actually invest in the infrastructure. You need to be able to reliably backtest your strategies and your generation forecast. So making sure that you have the data infrastructure needed to be able to simulate what historic performance would have been, right? You need to have, you need to make sure that you have everything in place such that you are actually able to simulate what results you would have had in the past. So given the data that would have been available at that time, but also being able to run a backtest using the exact same code as you'd be using in production. And then those are the typical steps you also need to be able to handle, right? So both the backtesting side as well as the production side. Data storage to machine learning infrastructure to the API which we use to expose our products to the customers. So in terms of to get into technologies a bit, right? So we are a Python shop, as you can call it, right? Almost everything we do is written in Python. We actually use Google Cloud, and like I said, right, a huge variety of other managed storages, managed solutions for storage. So from Google BigQuery to Cloud SQL to tools used for scheduling like Airflow. Like it's quite large diversity of tools you need to actually build and release a product like this.
So at the risk of exposing more of my ignorance here, when I hear Python, more of a scripting language and things like that, that tells me that speed, like computer speed, may not be of the essence because you're not optimizing down to the language. Is that a misconception on my part? Or is that, like I would think you'd be lower level languages if you want to go faster. So is speed not relevant to these models working at the same time? Or
so
not that?
I think in generally, Python can go really fast if you know what you're doing. At the same, so definitely, like, that's not a major issue. Also, it's the go-to language for typical for machine learning products, right? Or for machine learning tooling. It's like by far the leading product for that, or the leading language for that. Then, in terms of computational efficiency, the energy market is by no means at the level of efficiency or velocity as, for example, the stock exchange, right? So we're not talking nanoseconds here at all. So no, that's not the case at all. No.
And then you talked about running multiple models at the same time. You have some scale there. Is compute a consideration? So do you see, we see a couple trends, right? You see the renewables growing, so the amount of data and things coming in, but at the same time, compute generally improves over time as well. Your ability to get, cheaper, faster, greater access to compute generally improves year over year. Is that impactful to the business?
Yeah, definitely. So, over like you see this seep through everywhere in the industry, right? I think one of the fundamental things is that as storage and compute grows cheaper, like all of the fundamental things driving the market or being like feeding everything done in the market is improving, like weather forecasts, right? That's super depending on availability of cheap compute. As well as just sort of the digitization of the entire energy landscape. Like as storage is getting the rise of managed services on cloud providers, like all of that is impacting everything that's happening on the market. You see these little trade shops entering the market where just a couple of people with a cloud account and some trade licenses are being able to efficiently trade in a couple of months, right? So all these type of things you see happening and that are really, I think, interestingly disrupting the market. So yes, the fundamental thing happening of cheaper compute, cheaper storage is having a very big impact.
Well, as we try to pull this all together to bring our interview to an end here, I guess we talked about the markets you're in. We talked about the traders. So maybe pull this together from a trader perspective. Who are folks all already aware of what you're doing, or is this a new and emerging for traders to find out about your technology, or pretty much is this standard for the course today?
Yeah, so generation forecasting, I would say, is not new. So there's players that have been doing this when the first windmill was built in Germany 20 years ago. I think what's important to realize is that back in the day when you had tens of megawatts of renewables active in the market, they weren't moving the needle when it comes to market movements. But with the increase in penetrations of solar and wind power in our markets, like I already said, the correlation of you having a wind or solar portfolio and the market being relying on 80% wind and solar, the correlation is going to increase. And with everyone doing this now, what you will also see is that when there is a surplus of wind in the Netherlands, it's also going to be there in Belgium, Denmark, and the north of Germany. So in the past, for example, Germany had lots of wind and solar and neighbors didn't. they were able to send away surplus or buy from other countries via the interconnectors to solve their imbalances. But this does not hold anymore if everyone is being on the wrong side at the same time. And so therefore, trading will just become a lot more volatile and therefore dynamic. And I think the challenges, the threats on losing money on the short-term markets will increase, but also the opportunities, right? So in trading, there's often the ones who are on the wrong side, but there's also the ones who are on the right side. So it's really, I think being good at this goes both ways, right? So you're preventing a threat, but you're increasing an opportunity. And I think that's very important to realize when you are trading renewables in the future. And the volatility or the intermittency shows another trend we are foreseeing, which is in the past, you would have a fairly high certainty that you can sell your megawatt hours at a certain price. And for example, day ahead dips were manageable, whereas as we have seen in this spring, we can have day ahead prices in certain markets going to minus 400. And in the future, this will be even more, and it will happen more often. And suddenly, if you have promised to an off-taker that you will buy his power at a certain price, but you have to sell it to the market at minus 400, this day can ruin your profits for a month. And so suddenly, it's not only about selling or buying someone's megawatt hours for the next year or two and selling it to the market. It's really about managing that correlation that you have with the market and managing those price fluctuations by means of flexibility. And by flexibility, I mean you need to have the contracts, the technical capability and the IT systems and the connectivity in place to be able to be flexible on the trading markets, so day ahead, intraday ahead, the financial markets, but you also need to be capable of having flexibility in the physical market. So when the intraday market is closed, that you're actually able to steer physically on your position. And so I would say we are moving away from the megawatt hours. That's where the business used to be, into a combination of megawatt hours and managing the megawatts, so the flexibility. And of course, batteries will play a part, and they will solve it at some point. But we still have to install those hundreds of megawatts of batteries that we would like to have. And just like in onshore wind, you also have to make sure you get your policies and your regulations and your certifications to be able to build those assets.
Well, I think it's been a really amazing conversation. I want to thank you both for coming on. Thanks to Dexter Energy for letting you both come on the show today. It's been fantastic. Thank you so much. For our audience, we hope you've enjoyed this episode of Insider's Guide to Energy, the Data Science series. We look forward to talking to you again next time. Bye-bye.